Well, hello. We are now in starting Unit 6, working on polynomials. So our ultimate goal for this unit is to be able to factor polynomials, solve all types of polynomials, graph them, determine characteristics and behavior, domain and range, and all that good stuff. So we're kind of combining things that we've done throughout the year so far, and now we're looking at bigger degree polynomials. So we're not just going to be graphing our parabolas and our x squareds. We're also going to be graphing cubics, x to the thirds, quartics, x to the fourths, and we need to be able to factor those and solve those. Okay, so it's kind of, like I said, a mixture of things that we've done so far now to a bigger degree. All right, so at the end of today's unit, you should be able to classify a polynomial in standard form by the degree and number of terms. Graph a polynomial on your graphing calculator. If you don't have a graphing calculator, please pull up wabbit.com. Yes, that is Wabbit with a W. Wabbit.com, so that you can take a look at some of the graphs we are doing. It is free. You should also be able to describe the end behavior of a polynomial based on its degree and the sign of the lead coefficient without a calculator, just by looking at the graph. Okay, so those are our goals. So let's get started. So we're just going to take a look at some naming concepts first. So remember, a polynomial function is just a combination of terms. It could be many terms, it could be one term, whatever. And we always write it in standard form where you're going from the highest degree down to the lowest, meaning they're going in order of exponents. Now we have an x cubed, an x squared, x, and constant. You're not always going to have one of everything in each polynomial. For example, let's say you have something like this. You've got a polynomial where it's 2x to the fourth plus 3. Okay, so I don't have every single exponent given. I don't have an x cubed term, an x squared term, a quadratic term, or a linear term, my x. And that's okay, but just know that no matter what, when you're writing it, you have to go from highest degree, biggest exponent, down to the lowest on the left to right. Okay, so it tells us when I'm saying highest degree, the degree of a polynomial is the largest degree or exponent of any term. Right, and the name assigned to each degree is listed in the table below. So take a look at this. I'm hitting things. I don't know what I'm hitting. Hold on, I need to, there we go. Okay, so something that's a degree 0 is called a constant. It's just a number. All right, so in our first example, degree of 0, it's a constant, it's just a number. All right, we'll come back to the last two columns in a minute. A degree 1 has just a plain old x because the exponent is 1, and that's linear. It's a line. We've seen that before. When you have an x squared, that's a degree 2, also called a quadratic. Okay, now you might have something else in there. I might also have a, like, I could have 4x squared plus 3. That's still a quadratic. I just have more terms in it. Okay, but the whole point is anything that has a biggest degree or biggest exponent of 2 is going to be a quadratic. They all just look different. If your highest exponent or degree is a 3, that is a cubic, as we see in this example down here. Degree of 4 is a quartic, and degree of 5 is a quintic. Okay, quin meaning as a prefix for 5, and quarter prefix for 4. Our last two columns is then going farther and saying number of terms. Okay, because as I said in this example right here for the quadratic, the one you were given just had one term, a monomial. All right, we could also have a trinomial quadratic where I have x squared, x, and 3. I have a quadratic, a linear, and a constant. I could also have a binomial quadratic where I just have the x squared and the x term, or the x squared and the constant. Okay, so this back here, the number of terms, doesn't determine the degree, it just tells you how many terms are in there. So if there's only one term, it's a monomial. If there's only 2 terms, it's a binomial. 3 terms is a trinomial, and anything bigger we say polynomial of 4 terms, polynomial 5 terms. That's the correct way to do it. Now do keep in mind though that the number of terms cannot be bigger than the degree. Okay, so sorry, repeat. The number of terms can be bigger by 1. Okay, so if you look at this, if it has a degree of 0, the most terms it can have is 1. Yes, we can write another number, but after it's simplified, you're still going to have just a number. There's no variable term in it. Something with a degree of 1 can have at most 2 terms. Something with a degree of 2 can have at most, saw this right here, 3 terms. If you have a degree of 3, you can have at most 4 terms because you would have the cubic, you would have the quadratic, you could have the linear term and the constant. So the degree is 1 less than the number of maximum number of possible terms in there. So just so we don't think we're in this huge long quadratic with 10 million things. No, you can have at most 3 different terms, the quadratic, the linear, and the constant. All right, a quartic, a degree of 4, can have at most 5 different terms, and a quintic, a degree of 5, can have at most 6 different terms. Doesn't mean everyone's going to have 6 different terms, though. I could write a monomial quintic. X equals the negative 2x to the 5th, and that's it. Okay, it's a monomial. There's one term, but it's still a quintic because that is a degree of 5. The exponent is 5. All right. All right, so what we need to do now is practice. Let's write each of the polynomials in standard form, then classify it according to the degree and number of terms. So you're going to rearrange it so you're going highest exponent on the left down to lowest exponent on the right. Tell me the degree, and then tell me the number of terms. Okay, so pause the video and I want you to try this on your own, okay? I'm going to pause it and do it too so that when you press play again, the information will be on the screen, so please pause. Yes, I'm talking to you. Pause the video. And we're back. Okay, so take a look. Now you'll notice in some of them, as you're moving them around, you had some simplification that could be done. I could combine some like terms. So looking at my first example, I just rearranged it. Oops, sorry, that should be a negative 7x. I apologize. Okay, so 5x to the 4 minus 7x. It's a degree 4 because the biggest exponent I see is a 4, and it's a binomial because I only have 2 terms. All right, the next one, you could combine your negative 4x and positive 2x to give you negative 2x. So you want to actually go ahead and do that. All right, so I have a degree 3 because the highest exponent is 3, and it's a trinomial because I have 3 different terms. The next one, I could combine some things, and I have a binomial, degree 1 because the biggest exponent is a 1. It's a linear, it's a line. Our next example, I could combine, and I have a degree 3 because x cubed. And then I also have a trinomial because it's only 3 terms. And then I have a degree 5. My biggest exponent is 5, and it's binomial because I have 2 terms. Okay. All right, moving on. All right, so let's talk about end behavior. And we've discussed end behavior before. It's pretty much what's happening as a graph is continuing on forever and ever to the right and forever and ever to the left. Okay, and we've said, all right, make sure you know which way your arrow is pointing essentially. All right, but let's talk about polynomial functions. Really important to know first because we're going to start to look at different shapes. The graph of a polynomial function is both smooth and continuous. So by smooth, it means the graph does not contain sharp corners. So in the picture on the right, you see all these like sharp little turns here. That's not a polynomial, okay? It's not going to be a polynomial function. It doesn't fit into any of our patterns or x cubes, x to the 4th, or anything like that. And by continuous, it means a graph does not contain any holes or gaps. All right, we will look at the concept of holes later on this year as we start graphing rational functions. But for right now, we will not be seeing any holes, okay? So essentially, the key is you can draw it without lifting a pencil from the paper. So on the left is a polynomial function. I know there's no arrows, but it's just a smooth, and this is a cubic. Okay, on the right does not represent one. Okay, so what I would like you to do right now, using your graphing calculator, if you don't have one, go to wabbit.com. And you can use that one. All right, so it says using your graphing calculator, complete the following table. Number 1 is done for you as an example. And I'm going to do this with you, just kind of talk you through it so you can pause and do it on your own if you want to. All right, so the first thing we want to do is graph it. So when we graphed this right here, here's what it looks like. It's asking us the degree, which we can do without graphing, and it's asking us the lead coefficient, which we can do without graphing as well, just by looking at the equation. So it's degree 2 because that's my biggest exponent, and the lead coefficient is the coefficient in front of that biggest term, the first term on the left. Now, the key from this is to figure out end behavior without graphing, all right, but that's what we're going to discover right now. But looking at it's a quadratic and both the arrows are pointing up. So as x approaches infinity, so does y. And as x approaches negative infinity, so does y as well. Okay, so I'm just going to do some general sketches for these. If you do number 2, it's a quadratic with a negative in front, so I know it's going down like this. It's sad. So it's a degree 2 as well. My lead coefficient is a negative 1. And my arrows are pointing down, both of them. All right, so if I graph my next one, 2x to the 3rd minus 3x squared minus 2. Zoom 6, because I shouldn't need a crazy window. I can adjust it if needed. You get something that looks like this. So here's my x and y. Okay, it kind of comes up, curves back down, and goes back up again. Okay, that's a cubic. So my degree is 3, because that's the biggest exponent. My leading coefficient is 2. So let's look at our end behaviors. My left arrow is pointing down, and my right arrow is pointing up. All right, my next one, negative x to the third plus 2x squared plus 5x minus 6. Zoom 6. So just a heads up, when I'm recording, I can't pull up the online calculator. It won't physically record that. It won't show up. It's only going to record what's showing in my smart notebook. So that's why I'm not showing you my calculator. Just a heads up on that. All right, in this one, it looks something like this. And you can, be graphing with me to check. It goes like this. So it's a cubic again, but notice my arrows are in reverse. My right arrow is pointing up. My left arrow is pointing, my left arrow is pointing up. My right arrow is pointing down. All right, also a degree of 3. My leading coefficient is negative 1. All right, x to the fourth minus 4x squared. Take a look at my graph. Okay, and this one looks kind of like a W, and that's going to happen. And we're going to do more time and spend more time in class investigating the general shape of each one, so you can make predictions. So for right now, we're just kind of focusing on the arrows, the end behavior. But here's the shape. So it's a degree 4, and the leading coefficient is 1, and both of my arrows are pointing up. All right, now I'm doing a negative x to the fourth. If you've noticed, we're kind of alternating. We're going through each example and we're alternating a positive lead coefficient with a negative. And you should be seeing a pattern here. If you're not already, go back and take a look at it. Okay, so this one is going like this. Okay, and you have an extra lump here, and we'll talk about the different looks of a quadratic, quartic, and everything that stays consistent, but both arrows are going down. So degree 4 leads to negative 1. Both arrows are going down. All right, the last two quintics. So I have x to the 5th minus x to the 4th minus 2x to the 3rd minus 3x plus 2. I take a look, draw this one over here so I have room. Oh, interesting. Okay, so it looks like this. It's going up. It's coming down. It's kind of got this weird like kink in the middle thing, and we'll talk about that too. All right, but big thing is my left arrow is down, my right arrow is up, leading coefficient of 1, degree 5. My last one, degree 5, leading coefficient negative. So we've got a negative x to the 5th. I've got a positive x to the 4th, a positive 2x cubed plus x squared minus 4. Okay. All right, so here's this last one. Oh, okay. Something down like that. Okay. Left arrow's up, right arrow's down. All right, so we want to draw a conclusion. There is a pattern on here if you can see it. There's a couple different things to talk about that are going on. All right, so if you notice, look at all of your even degrees first. So degree to the quadratic and the quartic, the 2s and the 4s. What do you notice about both of the arrows? Yes, they're both going in the same direction. They're either both going up or they're both going down. But when you have an even exponent, even degree, your end behavior is going in the same direction. And that leading coefficient will tell you which way they are pointing. So if you can go look at example number 1 and example number 5, that's positive leading coefficients with an even degree. They're both pointing up because they're positive. Okay, so we see that. When it's an even degree with a positive coefficient, they're both pointing up. Examples number 2 and 6, when it's an even degree but a negative coefficient, both arrows are pointing down. Okay, so even degree tells us, hey, they're pointing in the same direction. Positive is up, negative is down. When they're both odd, if you notice, our x cubes, our cubics, and our quintics, our x to the fifths, they're going in opposite directions. One is up, one is down. All right, and there's an easy pattern to figure out which way it is. If you have an odd degree and your leading coefficient is positive, so in example number 3 and in example number 7, the left arrow is down, the right arrow is up. When they're both, or when it's odd and they're negative, the coefficient's negative, it's vice versa of that. Oops, I don't know where that came from. Now, easiest way to remember those, odd, okay, even going in the same direction, either positive or negative, odd going in opposite directions, and the leading coefficient tells you the direction of the right arrow. So for example, when it's a positive leading coefficient, my right arrow is going up towards the positives. Therefore, the left has to be going down. If it's an odd degree and it's negative leading coefficient, my right arrow is going to the negatives, therefore the left is to the positives. So that's how I kind of always remember which one's which. Look at your right arrow for those odd degrees. Okay. All right, so here's what I'd like you to do right now. You're going to pause the video. You're doing this on your own. Please go ahead and just without your calculator, put those down. You're going to just describe the end behavior, and you can just draw the arrows. Like you can draw, hey, like an up, up. I'm not saying that's one is, but just kind of draw up, 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 down, whatever. Okay? All right, pause the video, please. All right, so let's take a look. Now you had to be careful because if you notice they weren't all written in standard form. So really it would have been easier to go ahead and rewrite them in standard form, or just make sure you're looking for the biggest degree and the coefficient in front of that. So like in g of x, this last one right here, it's an x cubed and that leading coefficient's negative, which is why my right arrow is down. Don't think, oh, positive because of that. It's the coefficient on your greatest degree, so probably best to write them in standard form first. All right, so let's bring the doggy over to the water bowl so we can drink and we can check our answers. It was just really fun to do that. Okay, so as you can see, yay, I got them all right. Okay, take a look. If you have questions, please bring them to class. All right, so turning points, we're almost done, guys. This is real quick. We're going to practice calculating turning points in class. But what you need to know about turning points, and we've talked about it before with our quadratic, is where the function's changing direction. It's changing from increasing to decreasing or decreasing to increasing. All right, now you'll notice in this first example, there are no turning points. So yes, it's slowing down here, but it's not actually changing direction. And it's not necessarily constant. It's kind of very slowly, but there's no turning points. Versus over here, I have two. Here's my first, here's my second. Now, both of these actually represent cubics. So they're both x to the thirds. The more stuff is after it in the original equation, the more change you'll see in the function. Like this is not much. It's like an x to the cube, and that's it. And we'll talk about that later. But this one has some more stuff in the equation. Right, but what's important to know is that a polynomial function of degree n is greater than or equal to 1, so it's not like just a constant. It has at most n minus 1 turning points. So my point being is if it's an x cubed, you can have at most 2 turning points. If you have a degree of an x to the fifth, you could have at most 4 turning points. Now some will have less, okay, just like we see these two cubics. One has 2, the other has none. So that's an at most thing. All right, so we can use turning points to also help us when we're looking at a graph to determine what the degree of the function is. Count your turning points and add 1. Typically it works, but once again, we'll talk about this in class. Okay. And then, oops, done. Okay, and the last thing is, so we can determine the degree sometimes by looking at the shape of the graph. There is also another method. We can use the difference to find the degree. So it says we know a set of data for a polynomial function, and this only works if we know the points, and we want to know the degree. So how do we get what we want? Math magic. All right, so here's what you do. Here's my table x's and y's. So what I want to do is find the difference between the y values for each combination of 2. And you just keep doing this until they're all the same. So like when I do a first set of differences, this is what I get, negative 39, 1. Okay, so now from here, I take those differences and subtract again. Negative 39 minus 1, or sorry, minus negative 39. 5 minus 1, 3, and you keep going. Now I have another set of differences. They're not the same, so I need to keep subtracting. 4 minus 40, negative 8 minus 4. And you keep doing that until you get them all the same. So you see how in this last row they're all 24s? So you count how many times you went through and did that. 1, 2, 3, 4. So since it took me 4 times to get the same differences, it's an x to the 4th. Okay? Nothing to worry about too much, just kind of a little trick to know about. All right, so in class, we are going to do a little more with polynomials, talk about our turning points a little bit more, and we're going to practice identifying end behavior and all that good stuff. All right, so please bring your questions to class. We are done.